Meet Isaac Newton, a Cambridge mathematician who turns a thin Latin book into a new rulebook for reality. In London, in 1687, the first edition of Philosophiae Naturalis Principia Mathematica lays out 3 laws of motion and a gravity law that makes the same force pull apples down and keep the moon in orbit. The Principia spreads through the Royal Society and Europe, and it makes Newton famous while also making rivals watch him like a threat. Days later, Newton forces a beam of sunlight through a glass prism and shows that white light splits into a spectrum. Then he builds a reflecting telescope to escape the color fringing that ruins ordinary lenses. In 1672, he sends his results to the Royal Society, and the room turns hostile when Robert Hooke and others accuse him of missing key explanations and stealing ideas. Newton answers with icy letters, pulls back from publishing, and treats criticism as an attempt to erase his name. Meanwhile, in 1665 to 1666, the Great Plague empties Cambridge, and Newton retreats to Woolsthorpe Manor in Lincolnshire to work alone, while England counts the dead by the thousands. In that isolation, he pushes new methods for calculating change, tests gravity ideas against the moon's motion, and uses window light and homemade tools to keep experimenting when universities shut down. The solitude accelerates his breakthroughs, and it also trains him to treat secrecy as protection and isolation as power. That same hunger for control follows him into London, where he later becomes master of the mint and sends counterfeiters like William Challoner to the gallows after relentless interrogations and evidence building. In the 1690s, his private papers fill with frantic handwriting. He sleeps badly, and he writes paranoid letters accusing friends of plots, showing how easily his need for order turns into fear. He wins priority fights, outlives Hooke in 1703, and dies in 1727 as a national hero in Westminster Abbey. Yet his story keeps circling back to loneliness and the terror of being forgotten. But how did they get here? Let's start from the beginning. Before the apple, before the fame, before the wars over credit. After the mint and the feuds, the story rewinds to Woolsthorpe, Lincolnshire, where Isaac Newton is born on the 25th of December 1642, the same year England sinks into civil war. His father, also named Isaac Newton, dies before the birth, and family notes describe the baby as so premature and small that he fits in a quart mug. That first fact of his life is absence, and it teaches him early that survival means holding tight to whatever can be controlled. 3 years later, in 1645, his mother Hannah Askew marries the older rector Barnabas Smith of North Witham and moves into his house, leaving Isaac at Woolsthorpe with his maternal grandmother, Marjorie Askew. The separation is not a metaphor. It is a road out of the village, and a child watching a parent choose another home. The result is a boy who learns to keep feelings private and to treat solitude as a safe room he can build from rules and routines. Meanwhile, in the mid-1650s, Newton is sent to the King's School in Grantham and lodges in the house of apothecary William Clark, where jars of herbs, acids, and tinctures sit within arm's reach of a curious student. He fills notebooks with drawings and builds devices, wooden models, kites, and sundials. Because mechanisms do what people do not. They repeat reliably. The cause is loneliness, and the effect is a private inner world where time, motion, and hidden processes start to feel like problems he can solve. By 1659, his mother pulls him back to Woolsthorpe to run the family farm, but neighbors later recall him drifting from market and fields to read, calculate, and tinker, failing at the work he is supposed to inherit. The failure creates leverage. His schoolmaster Henry Stokes and his uncle William Askew press the family to send him back to study, arguing that his mind fits books, not crops. In June 1661, Newton enters Trinity College, Cambridge, as a subsizar who pays with service, and he watches the wealthier students while quietly planning to outrun them. Just as the next chapter brings the university's tools, rivalries, and the shutdown that will force him inward again. In the summer of 1665, Trinity College closes as the Great Plague spreads, and London's weekly death totals climb into the thousands. And Isaac Newton leaves Cambridge with notebooks, a few key books, and blank paper. He walks back to Woolsthorpe Manor in Lincolnshire, and turns the rooms that once held his childhood silence into a quarantine laboratory, where no tutor grades him and no rival interrupts him. The same need to control that drove his boyhood contraptions now drives a new rule. He shows his work to no one, and writes as if the world is unsafe. Days later, at Woolsthorpe, Newton fills pages with what he calls fluxions, treating quantities as things that flow in time so he can compute slopes, areas, and changing speed without waiting for a teacher's method. He pushes beyond the standard geometry of Cambridge by using infinite series and by matching differentiation with integration as inverse operations. Because plague isolation gives him uninterrupted hours to chase motion as a problem of pure order. The more the pages multiply, the more he locks them away, because he expects criticism to feel like the humiliations he survived as a child left behind. That same winter of 1665 to 1666, Newton darkens a room at Woolsthorpe, cuts a small hole in a shutter, and sends a narrow beam of sunlight through a glass prism onto a wall. He measures the colored band, and concludes the prism does not dye the light, because the colors spread by different amounts, and can be recombined, meaning white light is a mixture of rays with different refrangibility. The experiment gives him a new kind of certainty. Light as revelation. But it also teaches him a new kind of secrecy, because a claim this sharp invites public argument. Meanwhile, in 1666, Newton links his calculus pages to the sky by asking whether the same pull that drops objects near Woolsthorpe could extend to the moon's orbit, and he sketches the problem as a testable comparison of falling distance and circular motion. His private notebooks mix these mechanical questions with coded notes on alchemy and scripture, because he trusts systems more than people, and he wants a universe that cannot betray him. In 1667, as Cambridge reopens, he returns to Trinity with his prism results and his fluxions kept mostly private, and the choice to reveal them or defend them starts the next battle with institutions and rivals. Days later, back in Cambridge after the Woolsthorpe years, Newton turns his fear of exposure into hardware by building a reflecting telescope in 1668, grinding a concave metal mirror from speculum metal instead of trusting flawed glass lenses. In 1669, he becomes Lucasian professor at Trinity College at age 26, and he sends news of his instrument toward London because a device can speak where he will not. The same mind that hid fluxions now bets his reputation on polish, alignment, and a small tube that makes distant objects sharp without the rainbow fringes that bothered every refracting telescope. That same year, Newton's reflector reaches the Royal Society through intermediaries, and by early 1672, the Society elects him a Fellow after the instrument impresses with bright magnification in a compact form. On the 8th of February 1672, his paper on Light and Colors is read aloud at the Royal Society in London, arguing that white light is a mixture of rays with different refrangibility, and that a prism reveals what is already inside the beam. The applause lands like a spotlight, and the room's questions turn his private prism experiment into a public claim that can be attacked line by line. Within weeks, Robert Hooke, curator of experiments, sends Newton a critique in letters, pressing that the color effects come from modifications of light and implying Newton overstates novelty, and Newton reads the words alone in Cambridge as if they are an accusation of theft. Newton drafts long replies to Henry Oldenburg, the Society's secretary, insisting that his experiments separate colors that are already distinct and that prisms do not create them, and he treats every objection as a threat to credit. The dispute turns technical points into personal danger, and Newton's old habit returns as he begins to consider silence safer than publication. Meanwhile, in 1675 to 1676, Newton keeps answering and retracting in cycles, sending guarded clarifications to Oldenburg while privately writing that he wants to withdraw from the trouble of disputes that feel endless. As his public work becomes contested, He shifts nights into locked notebooks on alchemy and biblical chronology, searching for rules that cannot be voted down in a meeting room. The same defensiveness that protects his discoveries now narrows his world, and the Hooke conflict leaves a residue that sets up the next chapter. Newton will wait, then return with a book designed to overpower rivals rather than negotiate with them. In 1676, Newton stops writing to the Royal Society about light and pulls back into Cambridge, and by November 1679, a letter from Robert Hooke reopens the wound by asking how a falling body might curve into an orbit. Newton answers with a sketch of a path bent by Earth's rotation, and then pivots to what he trusts more than conversation: calculation. Because Hooke's claim that he already has the true idea of orbital motion sounds to Newton like another attempt to take his work. Weeks later, Newton's mother Hannah dies in March 1679 at Woolsthorpe, and the mix of grief and rivalry hardens into a need to prove motion with a system so complete that no critic can pry a piece away. On the 22nd of August 1684, Edmund Halley rides to Trinity College, Cambridge, and asks Newton what curve a planet follows if the sun's force weakens with the square of distance, and Newton answers an ellipse, then admits he cannot find the paper and will redo the proof. That same autumn, Newton sends Halley a 9-page manuscript, De Motu Corporum in Gyrum, deriving Kepler's area law and elliptical orbits from an inverse square attraction, and Halley immediately reports the result in London because it beats Christopher Wren's prize challenge from January 1684. Halley's insistence turns Newton's private certainty into a deadline, and Newton begins expanding De Motu into a full treatise that he refuses to let Hooke frame as borrowed. Between late 1684 and 1686, Newton writes what becomes the Principia in 3 books, filling pages with Euclidean propositions, hand-drawn diagrams, and lemmas that turn forces into geometry because he distrusts the new calculus that rivals might claim as theirs. In 1686, when the Royal Society prepares Book 1 for printing, Hooke demands priority for the inverse square idea, and Newton threatens to suppress the entire section on gravitation until Halley mediates and keeps the project alive. The dispute forces Newton to tighten every proof and every credit line, and his need to control the story now drives the mathematics as much as the physics. In July 1687, Philosophiae Naturalis Principia Mathematica appears in London under the Royal Society's imprint, and Halley pays for much of the printing after the Society's funds are drained, then handles distribution while Newton accepts help but hates dependence. Newton's triumph is immediate among mathematicians, yet the Hooke quarrel leaves him bitter, and after Hooke dies in 1703, Newton will outlive and outmaneuver his memory, but in the early 1690s the cost arrives first. By 1692 to 1693, Newton sends erratic letters to Samuel Pepys and John Locke, accusing friends of betrayal, reports sleeplessness for nights at a time, and collapses into paranoia that pushes him toward a new solution. If ideas invite attack, power and office can enforce order. In 1696, still shaken by the sleepless paranoia of the early 1690s, Isaac Newton leaves Cambridge for London and takes the paid post of Warden of the Royal Mint at the Tower of London under Charles Montague. Days later, he walks through counting houses and markets where clipped silver coins fail by weight, and the government answers with the great recoinage of 1696 to melt old money and strike milled coins with lettered edges that expose tampering. Newton brings his old habit of certainty to the crisis by turning the nation's panic into ledgers, assays, and tolerances, and the work pulls him from private theory into public control. That same year, Newton oversees weighings and assays as cartloads of hammered coins arrive to be melted, and the new milled shillings and half-crowns leave the presses with crisp rims meant to defeat clippers. He pushes the mint like a laboratory by demanding exact accounts from moneyers, checking deliveries of silver, and tracking shortages that could mean theft, because a small loss per batch becomes a national scandal. The tighter he makes the system, the more he learns that order on paper drives crime underground, and he starts collecting names, addresses, and habits like data for an experiment that ends in court. Meanwhile, Newton targets William Challoner, a prolific counterfeiter who boasts in London coffeehouses, and even petitions Parliament with schemes to reform the mint while running illegal presses. In 1698 and early 1699, Newton builds a case by hunting witnesses in taverns and debtors' prisons, taking depositions, and confronting suspects with contradictions the way he once cornered an orbit with equations. In March 1699, the evidence reaches the Old Bailey. Challoner is convicted of high treason for coining, and he is hanged at Tyburn on the 22nd of March 1699, proving Newton can turn reason into punishment as efficiently as he once turned it into proof. Weeks after Challoner's execution, Newton's success hardens into rank when he becomes master of the mint in 1699, and he keeps the job for life while his identity shifts from scholar to state enforcer. In 1703, after Robert Hooke dies, Newton becomes president of the Royal Society and uses the chair to control credit and publication, the same rivalry impulse now aimed at Gottfried Wilhelm Leibniz as the calculus dispute turns personal. By 1712, the Royal Society issues a report on the invention of calculus that Newton quietly drafts himself, and in 1713 he locks his version of authority into the second edition of the Principia, setting up the next chapter's question of what his victories leave him with besides reputation. In 1714, after Queen Anne dies and George I takes the throne, Newton stays at the mint as master and becomes a public symbol of stable English order. That same year in London, he keeps late hours in his rooms near St. Martin in the Fields with stacks of mint ledgers beside drafts on biblical chronology and alchemical recipes, showing the same need to force hidden systems into rules. Meanwhile, the calculus dispute keeps boiling, and Newton uses his power at the Royal Society to shape the record, including the 1712 report that favors him over Gottfried Wilhelm Leibniz and turns a private fear of being erased into an official verdict. Days later, admirers repeat Newton's old line from his 1675 letter to Robert Hooke, "Standing on the shoulders of giants," as if it proves humility, while Newton's own actions make the phrase sound like a weapon that decides who counts as a giant. In 1713 and again in 1726, he oversees new editions of the Principia in London with Roger Coates and then Henry Pemberton, and he corrects details about comets and planetary motion, while refusing to soften the story of who discovered what. The result is a legacy that looks clean in print, even as his private cupboards keep filling with unpublished work that no one is allowed to question. Meanwhile, his health weakens, and by early 1727, Newton lives in Kensington, away from the mint's daily noise, as he struggles with recurrent abdominal pain that keeps him awake through the night. On the 20th of March, 1727, he dies in London at age 84, unmarried and without children, leaving a fortune of about £31,000 and an estate of papers so large that even his heirs cannot sort the science from the theology. The city keeps moving. Coaches, markets, church bells. While clerks and relatives begin sealing trunks that contain both the laws of motion and pages about prophecy. 9 days later, on the 28th of March 1727, Newton is buried in Westminster Abbey, and pallbearers include dukes and earls, turning a solitary scholar into a state monument under carved stone. The Abbey inscription praises the man who surpassed the human race, but the praise cannot show the locked notebooks of alchemy, the private timelines of scripture, or the rivalries that narrowed his circle as his fame expanded. The film ends by returning to the recurring objects. Prism light across a wall, the Principia's diagrams, the mint scales, and then to Woolsthorpe's quiet, setting up the final question of the documentary: how much certainty his ordered universe costs him in intimacy and peace.